talk about spherical coordinates. In spherical coordinates, we have one length and two angles. Our one length rho is just how long is your vector. It's just the length of your vector. Our number one angle is theta, which is the same theta as in cylindrical coordinates. Namely, it's the angle your vector makes with the positive x-axis. Then the new angle, phi, is the angle that your vector makes with the positive z-axis. Okay? So let's see where these new things came from. So if you remember in cylindrical coordinates, x was r cosine theta and y was r sine theta, right? Well, here it's something similar, except now we don't have r. So we have to sort of give ourselves r or find it. And the way we're going to find it is remember what r was. If you remember, r was the length that you traveled in the xy plane, okay? So we had our length that we traveled in the xy plane, and then our length that we traveled perpendicular to the xy plane in the z direction, which was just z. Here, it's very similar, except we don't have r, so we got to find it by saying, well, I have rho and I have phi. So what z or what r are functions of rho and phi. Namely, if I wanted to find z, I could just say it's rho cosine phi, right? That's just z. And if I wanted to find r, it's just rho sine phi, because that's going to be the component of r. Rho cosine phi is the component of rho that's going along z, and rho sine phi is the component of rho that's going perpendicular to the z-axis or in the xy plane, which is our r, right? So with these two things in mind, we can go ahead and rewrite x, y, and z just as we did in our cylindrical coordinates. But now instead of saying r, we say rho sine phi, and instead of z, we say rho cosine phi. And that's all there is to it. Okay? So you don't really have to memorize this anytime, or you can if you want to, but if anytime you forget it, you can just really quickly think about the dynamics and say, okay, well, this is phi, this is rho. If I wanted to find z, it's rho times cosine of phi, okay? And r is just rho sine phi, and then you just put in the cosine theta and sine theta in order to find x and y. So same goes with the finding theta and phi. Theta is still the same as our cylindrical. It's just the tan inverse of y over x. But now for phi, it's a little new, but it's not any harder. You just think about it. Well, what is phi? Well, I know this length, it's rho, and I know this length, it's z. So all I got to do is just find the inverse cosine of this over that, and I get myself my phi. Okay? So let's go ahead and do an example of a conversion just to see how this plays out. We have z equals x squared minus y squared. Okay, well, what is z? Well, I don't know. I'm not going to look at the formulas. I'm going to come back to the shape and look and ask and see, okay, well, what is z? Well, it's rho cosine phi, right? Okay, so it's rho cosine phi. Then I have x squared. Well, I'm going to do the same thing, and I'm going to get rho sine phi cosine theta all squared. And with the y squared, I'm going to get rho sine phi sine theta all squared. So now I can factor out my rho squared sine squared phi, right? And I'm going to be left with cosine squared theta minus sine squared theta is equal to rho cosine phi. One rho goes with one rho. Now, what I can do is make this a little simpler by remembering that cosine of 2 theta is cosine squared theta minus sine squared theta. So this is actually just going to be cosine squared theta. You got to remember your trig identities and stuff like that in multi. So, and usually what we're going to do is solve for things and set them equal to rho. Okay. So I'm going to write rho is equal to cosine of phi over sine squared phi times cosine of 2 theta. Okay? And that is my answer. So, as you can see, it's not it's not. It may be a little new if you've never seen the spherical coordinate system. It may be a little new, but it's not hard. So there you have it.